Thank you. Thank you. I would like to thank the organizers to invite me giving this talk here. So I'm going to talk about relationship between fluid circulation and earthquakes in the Forearc region of subduction zone. This is mostly based on experimental work we do in Lyon, and I would like to associate my postdoc Anne-Céline Gonzorn, who's been working with me for a bit more than 2 years, and former PhD student Hélène Pilorget, who contributed to that work. So when we talk about fluid rock interaction in subduction zone, we can cover a broad range of PT conditions and characteristics of the fluid. I'd like to distinguish it here two main conditions. If we are above temperatures like something around 700 degrees C, the fluids that are released from the subducting slab are going to contribute mostly to melting and arc volcanism. So this is not my purpose here. I'm going to talk about the region that is before this arc, the Forearc region, where fluids are generated in temperatures that are below this critical temperature. And what I will call fluids in the remainder is mostly aqueous fluid that are dominated by water plus a little bit of dissolved species. And so these fluids are thought to play an important role in the generation of earthquakes from the plate interface down to intermediate depth earthquakes that we've heard about this morning. So if we want to understand what's going on, we know that fluids are released because of dehydration reactions, because the plate is heating as it's going down into the mantle. And we suspect that these fluids, because they're buoyant, are going to go up. But there are many ways they can go up. And this is a sort of summary of what you can find in the literature. So you can see that some people like it to want to go back up along the plate boundaries, whereas some like to have it crossing this boundary. Stopping at some discontinuities. So if we really want to understand that, we need to have some knowledge of the porosity and the permeability of the metamorphic rocks that are constituting the slab and the mantle above the slab in these conditions. So I'm going to show you that we can try to measure the porosity and estimate the permeability of metamorphic rocks. So obviously fluids are likely involved in the earthquake cycle. This comes from models that were developed in the 80s by Sibston and then by Sleep and Blampied in the 90s. The reason for that is that in a given time frame, we have an earthquake cycle that sets up. If we can increase the stress and then release it by catastrophic event, that is the earthquake. And the kind of model they develop states that because we are at great depth, we need to have a mechanism that allows for the fracturation. And the mechanism that is most likely, according to them, is that you can increase the fluid pressure to a value that is close to the hydrostatic, lithostatic pressure. And then it is very easy to get close to the frictional criterion where you can break the rock. And associated to this mechanical behavior, you need to have an evolution of the porosity of the rock. So along with the earthquake cycle, you need to have a porosity cycle by which you increase the porosity during the deformation, the very short deformation during the earthquake. So because you increase the porosity immediately after the earthquake, you decrease the fluid pressure, and then you can start re-increasing this fluid pressure by a mechanism that can be a sealing of the pores by a pressure solution, for example, or any deformation mechanism that you can imagine that would close the pores. So porosity, again, is an important parameter in understanding the earthquake cycle. So another kind of observations that is not exactly earthquakes, but is related to earthquakes is, and where fluids are likely involved, is what I call slow seismicity, low frequency events, episodic tremor and sleep, slow sleep events, etc., that take place quite deep on the plate interface, and those characteristics are often make people think that fluids are involved in the generation of these slow events. And it is thought that these slow events are often precursors of large megathrust earthquakes. I won't comment too much this plot because these are not my figures, but this is an example of people observing low frequency earthquake or episodic tremor and sleep before the large Tohoku Oki earthquake in 2011. So this is the kind of picture that people draw about this context. And I took another one because I think it's very colorful and spicy. And what I find interesting in this picture is that these authors argue for the fact that you need fluids to feed the bottom of the seismogenic zone in the subduction zones. And once you've started feeding the bottom of the seismogenic zone, you can start having slow sleep events that eventually will lead to megathrust earthquakes. So my main interest here is trying to understand how we can get fluids to this region here. So all this happens in a very complex system. So this is a seismologist's point of view, which is more kind of mechanical, where you have frictional asperities and areas where you can have fluid circulation and slow sleep. This is the view of the petrologist on these areas. So for a petrologist, you will have different rocks in this context, from sedimentary rocks, especially important close to the trench and in the accretionary wedge. You will have, of course, the oceanic crust, which is composed originally of basalts and gabbro that will transform into blue schists and eclogite as we go down and dehydrate. And in this region here of interaction, you can get even more complex situation where you start having the mantle wedge here that is exposed to fluid circulation and will become serpentinite, so will form serpentinites. And all these rocks can, of course, be more or less transformed because of the intense fluid circulation that you have at the plate interface, and that will cause the formation of metasomatic rocks, often monomineralic with one phyllosilicate like chlorite or talc. So the nice thing about that is that it's not only a conceptual model and we can sample it. It means that we can go to areas like this, which are very nice actually to visit. This is in the Alps. This is an ophiolitic section that has been exposed to eclogitic conditions, and where we can find serpentinites and gabbros or basalts or blue schists or eclogites that have been transformed under subduction zone conditions. So we can then use these rocks to do our experiments. So the kind of experiments we do with these rocks is to experiments where which are not classical petrological experiments, in the sense that we don't want to try to destabilize the minerals that are in these rocks. The only thing we want to do is to have them interact with water and try to measure the transport properties like porosity or permeability, which are important for characterizing fluid circulation. So we do experiments in a high pressure setup to mimic the conditions of subduction zones. And the way we do that is we take a core of a given rock. So this is going to be a very small sample because we want to go to high pressure. We put that in a capsule. We embed it into a powder of the same rock. And we load this powder with deuterated water. So we just fill the porosity of the powder with deuterated water. We put that in a gold capsule, which is sealed under pressure. And then we make this aqueous fluid interact with the rock. And the problem with the fluid-rock interaction is that it's something that is elusive. If you don't use a tracer, once you take your sample out of your press and you open it, you will lose the fluid, so you will lose the information. Here, we use deuterated water so that we can use the isotopic exchange as a tracer of the fluid-rock interaction and use it to characterize the properties of the rock. So this is what a real sample looks like after the high-pressure experiment. So I didn't get wrong in putting the sample in the other direction. This is actually what happens to the sample because we have a very porous sample and a lot of water into it. It gets deformed a lot and it basically changes length and height during the experiment. We can recognize the core here that has been more or less deformed, and here the powder that has deformed a lot and has been slightly compacted. So then we have to use this isotopic tracer, and we use a technique which is called Raman spectroscopy to actually map the exchange of deuterium and hydrogen between the rock and the water. So this is what this technique looks like. So this is an example of Raman imaging on a piece of sample. So this is a map, 20 microns by 140 microns. So in this map, we take at each pixel corresponds a Raman spectrum. And in this Raman spectrum, we can observe vibrations that are due to the hydroxyl bond in the minerals, in these hydrated minerals. So this one is related to hydrogen. And if we substitute deuterium for hydrogen, we change the mass, so we change the characteristic frequency of the oscillator, and we find that there is a ratio of frequency which is close to the square root of the ratio of the masses. So this is about square root of 2, lower frequency of oscillation. And so we can observe also the substitution of deuterium for hydrogen in these minerals. So this is what a typical map looks like. We have area of intense interaction with a high deuterium to hydrogen ratio. And in some areas, here this is a crystal, a single crystal of antigonite. So this was in a serpentinite. And we see that in the cores of these crystals, we have actually diffusion profiles, and the cores have much lower deuterium to hydrogen ratio because this exchange is governed in that case by solid-state diffusion. So we can model these solid-state diffusion patterns and extract diffusion, solid-state diffusion coefficients in these minerals. So this is what we did for several minerals. I show here what we did for antigonite and chlorite, and we've now measured amphiboles and other minerals from the high-pressure rocks. I'm not going to comment too much about that. It's just I'm just mentioning to you that we have characterized these coefficients, and we are actually using it to measure porosity. So another interesting observation on the very same picture that I showed you is that when we compare the Raman map with a classical SEM image, so this is electron microscopy, just a picture of the texture at the surface of the sample. So we see here that we have a large crystal of antigride. This is a phyllosilicate, so it's very elongated. It's a bit like a clay mineral. And there are several interesting things we can see. We can see cracks here. So you could say, well, why bother about deuterium hydrogen exchange? We could use this kind of picture to determine the porosity. But the problem that the porosity we see at the end of the experiment is not the porosity that was active during the high pressure and high temperature experiment in the conditions of the subduction zone. And this is very clearly seen on these cracks, which are marked by yellow arrows. You see that these cracks actually cross-cut the diffusion profiles in the crystal. That means there was no fluid going along those cracks during the experiment. So this was inactive porosity at high pressure, and this is just cracking due to the decompression of the sample after the experiment. On the other hand, here we have a section of the crystal where we don't see much on the RCM image, and here we see that we have a clear separation of two diffusion domains in this crystal. So that means that there was here some kind of porosity that was active, and that fluid could penetrate this interface here and cause a double diffusion on each side. And actually, when we look with much higher resolution on SEM or in TM, we actually can characterize this porosity, which has the shape of different pores with negative crystal shapes. So this is very important to do this kind of experiment to actually characterize the porosity that is really active during the high pressure and high temperature experiment and what happens in subduction zone. So before going to using the experiments we do, what do we know about rock porosity in subduction zones? Well, there are two types of experiments that have been conducted thus far. Low pressure experiments that are just flowing gas through a rock that is slightly compressed. So these are restricted to pressures like 50 to 100 MPa. So we go down to maybe 3 kilometers with these experiments. This is done at room temperature, so there is no fluid reactivity as we could expect in a subduction zone. And on the other side, there are so this is the kind of experiment that are shown here, and then you use some systematic of relationship between porosity and permeability to make an extrapolation at 1 gigapascal, which would be 30 kilometers depth, and you find that everything is basically impermeable. Another way to characterize porosity is to do textural equilibrium experiments. So some have been done on quartz and olivine. You have, for that, to go to very high temperatures to reach equilibrium texture. And you can get this kind of pattern of porosity, which is governed by a single parameter, which is the wettability, the wetting angle of the fluid. You can model this, and often in doing that, little anisotropy is assumed. And of course, in the domain that we are interested in, we are right in the middle of this kind of experiment, and we are dealing with very anisotropic material like clay or amphiboles. And so this is why there are no data, basically, and what makes it difficult but interesting. So again, back to our experimental approach. So we take a chip of our core and natural rock, we put it in the capsule and in the press along with deuterated water. We increase the pressure, we then raise the temperature. We do that for a given amount of time. We collect the sample back, we cut it in halves, and we do an analysis on a polished section. So, and we take advantage of this isotopic tracer to try and get the porosity. So one way to look at this experiment is that we are actually increasing the pressure. So during this pressure increase, we have a large displacement of the piston in the press. So it means that a lot of the deformation that we see on this sample occurs during this first stage, and we call that an earthquake. It's a very large deformation that takes place in a short time. And then we increase the temperature, and we have a stage where we have some relaxation, and of course the isotopic exchange takes place at this time, and then we quench the system, first the temperature and then the pressure. And we worked on 3 different rocks. One is a blue schist that represents the metamorphosed oceanic crust. One is a serpentinite that represents the hydrated mantle wedge. And one is a chloride schist that we think represents very well the metasomatic plate interface between those 2 units. So then we quantify the exchange between the fluid and the rock. So the deuterium comes from the fluid, and the hydrogen was originally in the minerals. And the way we use it to quantify porosity is to put ourselves in conditions where the intracrystalline diffusion coefficient is around 10 to the minus 20 square meter per second. And in that case, the characteristic diffusion length by solid state is 20 nanometer. That means it's very small. So if we have very few grain boundaries or cracks in the rock, we will see very little interaction. We will see very low deconcentrations because we analyze with a beam size which is much larger than this characteristic length. And if we have, on the other hand, very high concentrations of deuterium, which are in these yellow to reddish colors here, it means that within 1 pixel, we have several interfaces from which the diffusion could take place from the interface between the fluid and the crystal. So it's one way to count the number of grain boundaries we have in the rock. So we just check by comparison with electron microscopic observation that this is pretty reasonable in some rocks. So here is a blue area. We see that we have crystals with very little fracturation, and then you go to these orange or reddish areas here, and you see that the crystals are riddled with little grain boundaries here that were probably active as a porosity during the experiment. So we can use our knowledge of the diffusion coefficient and time of the experiment to model this exchange, and actually we get a relationship between DDD over H ratio and the number of grain boundaries within 1 pixel, or the number of cracks within 1 pixel. And then we can go to the porosity if we make an assumption on the thickness of the grain boundaries. So we just multiply the density of grain boundaries by the grain boundary thickness that we assume, and we assume the grain boundaries thickness of about 1 nanometer, and we can give it a slight range, but it's a reasonable range for metamorphic rocks. So we have a nearly linear relationship between the isotopic ratio and the number of cracks, and so we can convert this image to a grain boundary density and extract porosity from that. So this is the results we get for all the rocks we've analyzed. So blue schist has the highest porosity, followed by serpentinite that suffered a lot of deformation. Then we have start having quite impermeable rocks. The most impermeable one is chloride schist, and followed by undeformed serpentine or well-recrystallized serpentinite. So immediately you can see that you have a broad range of colors which indicate a broad range of porosity. You can see that for serpentinite you have a large range of porosity depending on whether it is deformed or undeformed. So this can potentially fuel the earthquake cycle. And then we can use these data to extract quantitative values for porosity and try to guess permeability from classical relationships. I won't go into the details here. And we see so that chloride schists have fairly low permeabilities, porosities and permeabilities, whereas blue schist, that means the oceanic crust, has a porosity which is between 1 and 4%, and permeability is around 10 to the minus 19 square meter. We can compare that with available geophysical estimates of these values. So here I took values from a paper by Peacock and co-workers in geology, which relied a lot on seismological results from O'Day, Bostock and co-workers about overpressured oceanic crust in Cascadia. So they used this seismological data to guess the porosity of the oceanic crust in this region in conditions that correspond to the green schist to blue schist facies region, and they get values of 2.5 to 4%, which matches pretty well with the kind of value we extract from our experiments. And also they concluded that in order to maintain high fluid pressure in this region that causes a very anomalous VP to VS ratio, they need to have a seal at the top of the oceanic crust that has a permeability which is below 10 to the minus 21, which matches pretty well with the chloride schist we measured and that we infer to be a potential seal at the top of the downgoing slab. So I'll go, I'm nearly done with my talk. So we've set up a new method to constrain active porosities in rocks at high pressure. And an important result is that we have a broad range of behavior from nearly impermeable for the chloride schist to permeable for deformed serpentinites and blue schists, with porosity variation in response to this formation, which is important for establishing an earthquake cycle, for example. And this is the kind of conclusions we can draw from our measurements. It means that we have in the subducted plate in the oceanic crust a fairly large porosity between, say, 1 and 4%, especially in the blue schist facies. Over that, we have an interface that is a sort of permeability seal because we form schists like chlorite. Of course, when we go into the very deep areas, this seal may be reduced to a very thin layer of a few meters or maybe even less. And so you can imagine that at some stages, earthquakes are going to break this seal periodically and allow for fluid entering the mantle and causing a partial serpentinization there. And to finish, I'd like to put that into perspective with the observation of intermediate earthquakes. So I'll skip the stuff about the episodic tremor and sleep in Cascadia to focus on the comparison with what happens in northeastern Japan and has been observed by Kita and co-workers a few years ago. So they compiled the seismicity in this area. So this is the downgoing slab under northeastern Japan in Tohoku area. This is the double seismic zone with the upper seismic zone here, which is concentrated into the oceanic crust. You see that most of this seismicity stops here at the blue schist to glaucophane eclogite transition. And then we have complete dehydration to the eclogite here with absolutely no earthquakes in this region. And the way we interpreted the fact that the seismicity is mostly restricted to the area where hydrous minerals are still stable is that we have a sealed interface here, and all the dehydration that takes place here does not seem to trigger so much intermediate depth seismicity, but it's actually probably because we have a permeability seal that we can have an upward flow of the dehydration water that goes into this area and causes fluid overpressure and causes this intermediate depth seismicity. and I'm going to finish here. Thank you.